upload it as soon as it's done. So yeah, take a blank sheet of paper. We're going to start right away with a practice problem. And this problem is taken from, it will be from the next exam. So if you work through this, you'll be doing a little practice for the next exam. Let me pop up my little notepad, and you can just write down the problem, and then I'll give you a little chance to work through it on your own. Wrong button here. I'll give you a chance to work through it on your own, and then I'll demonstrate the solution. And there's my pencil. Okay, so here's your problem. We're going to do a little bit of the practice with combinations of functions. We have f of x equals x squared minus 36. That's your f of x. You have g of x equals x plus 6. So they're going to give you a problem. Give me f of g of x. What does f of g of x equal? Give you a little chance to think about that. And if you're watching the video, pause here. And I'm actually going to pause the recording just so I don't waste time on the recording. Okay, let's see. How would I approach this? Well, g of x is this. So I feed that into where I see an x over here. So here's how I might approach it. I'll say, okay, f of x takes something and squares it and subtracts 36. What is that something? Well, that something is g of x. So I feed g of x where I have the x. So I put an x plus 6 right here. Now take a blank sheet of paper, put your name on it, and I'm just going to do a few practice problems on that. Now, was this step at all unclear? We have g of x here. We take g of x and put it here, and whatever we do with his input, x, we do that to g of x. So now, multiplying that out, if you get this part, that's probably the rest is, well, cranking through the squaring of that. I'll walk you through that. But that's the most important thing, that you recognize this is g of x, and this goes where f of x was squaring its x. So this is where we put g of x. We turn that x into what g of x is, which is x plus 6. Another way to look at it would be, I take f and I have x plus 6 as my input. All right, let's go ahead and just multiply that out. I'll multiply the first. Well, actually, we'll write that out just to be clear. That's x plus 6 times x plus 6. If it helps to write it out, feel free to do that. That becomes x squared plus 6x plus another 6x plus the 36. And don't forget, we're also minusing 36 from that squared. Now this comes out a little easier. Look at this. The 36 subtracts out, and it becomes x squared plus 12x. If they said factor it, you could also say, well, that's x times x plus 12. If they wanted you to factor it. But both of these are good answers. That was your little starting practice problem. Any questions about that? Any trouble with that? As long as you write that out, that's your first practice problem. Don't have to worry about writing anything else on this paper until I come to another practice problem to ask you to write this out. This blank paper that with your name on it counts as your attendance. Remember, it doesn't matter if you get it right. Just that we worked through that one. Okay, special announcement. Special announcement. The review quizzes, exams 1 and 2. Review exams 1 and 2 are online, and they are open for you to retake. Well, you never actually took the online one. I did a version of that and gave you a hard copy. If you go online and work through the review exam 1 and 2 online, complete it, that score will bump up your exam score for exam 1 and 2. Open book, open notes will bump up your score. Yeah. No. I'll make sure that by doing it, you get more points. I'll treat it like an extra credit. You go back, review exam 1, exam 2. I was thinking of just curving it, but I thought, you know what? You'll do better on the final because it does have some questions on there by going through that and reviewing it. I could just say, oh, use that to review for the final. But I want to give you opportunity to bump up those exam grades. What happened in the system is the exam grades weren't being properly weighted on your grade, and so you saw a bump in that because the exam, some of you needed a little help. So I'm giving you your chance to bump up your exam grades. Okay? Yeah. Good question. November 12th. Same as a deadline for review exam 3, which is going to be reviewing this stuff. So that's next Thursday, right? Right, next Friday. Yeah, all the way till Friday. I don't want you to have to work on it on the weekend. So deadline Thursday, deadline Friday, I mean, get that done. And you can get it done beforehand. So any troubles on this particular problem? So multiplying. This is probably the hardest thing. Taking x plus 6 and feeding it, seeing what f plus g of x means. And remember, sometimes you'll see that as f dot g or f composite g of x. That means this. I like that notation better, but you will see this, f circle g, f composite g. I like that better because that makes it clear. Yes, I'm taking g and I'm feeding it into x's input. Okay. Few questions there in that text. How many stars are there in the galaxy? You go online and look, and any guess at what the number might be? How many stars in the known or in our galaxy? They say there are about 10 to the 11th, 10 to the 12th stars in our galaxy. You hear people talking about that? You go to a science show, yeah, there's 10, there's a 1 with 11 zeros after that. That's how big that number is. I remember as a kid, I can count to 1,000,000. No, I can count to 1,000,000,000. Well, my dad can count to Google, whatever that is supposed to mean. And then you realize later, what does that mean? Well, 1,000,000, 6 zeros. Billion, 9 zeros. All right? You count the zeros. Well, logarithms, you've been doing logarithms ever since you were a kid, or read things about how many stars there are, and you said it's 10 with 11 zeros after it. What you're basically saying is that's the power of 10 in that huge number. Well, it happens to be that they believe from the observable universe so far that there are about 10 to the 23rd stars in the universe. Now, anything with more than 6 zeros after that, my mind just thinks, well, that's a really big number. Like, what if there's a billion grains of rice? How big would that pile be? I don't know. Might be a pretty big pile, but 10 to the 23rd, that's a really big pile. A lot bigger. Here's a little test for you. They do this on one of my favorite YouTube channels, is Number File. They said, just for fun, put on a piece of paper from here to here, what would be 1/1000th of the distance here? Well, let's just do that on our little whiteboard here. What would be 1/1000th of the distance across this whiteboard? And in the number file, they say, well, a lot of people will say, yeah, it's somewhere over here. let's just do that really quick. You just ask, yeah, it's somewhere over here, 1,000. Well, realize, wait a minute. Let's see. 1/2 would be about here. So this would probably be more like 1/10 would be about right. 1/10. Well, 1/100 will be a tenth of that. So half of that, 5 pieces there. 1/10 of that would be about 1/100. 1/1000 would be 1/10 of that. So half. So 1/1000 would be about right there. Now, I don't know if you were thinking that you got 1,000 of this board, would it get basically really, really close, really tiny number? Because you're talking 1/10 and 1/10 of that and 1/10 of that, which is exponential getting smaller and smaller. How about this question? If there, why would we said there's 10 to the 23rd stars in the known universe, estimated. How many atoms in the known universe? Well, all I need to know is, well, how many atoms in a star? Say 10 to, I think they think atoms in a star about 10 to the 60th atoms in a star. 10 with 60 zeros at it. So, to calculate the numbers of atoms in the universe, well, 10 to the 60th times 10 to the 23rd. Can you do the multiplication? 10 to the 60th times 10 to the 23rd. Just add 60 and 23. You get 10 to the 83rd. We've turned multiplying of huge numbers into simply adding the exponents. And that's the power of exponentiation, is multiplying huge numbers. And the number they tell me here, if I go to one website, it says about 10 to the 82nd atoms in the observable universe. That's between 10 quadrillion vigintillion and 100,000 quadrillion vigintillion. So vigintillion is apparently somewhere around 10 to the 70th. Vigintillion. But when we think of it, we just think of, well, there's 78 or 80, 83 zeros after that. Really, really big number. So that's what logarithms are. Just basically saying there's so many zeros after that number. So let's think carefully about a few logarithm things to get this in our mind. And they are related to exponentiation. This chapter, logarithms, always comes after, in algebra, the exponent chapter, because they're related. And we'll see that, well, just like we were saying, that inverse of 2 to the x, well, what we're looking for is a function. This was our exponential function, y equals 2 to the x. Well, what would be the inverse of that? Remember we talked about inverse functions? Remember how we do an inverse function? We switch the x and the y. So I'll do inverse. We switch the x and the y. X equals 2 to the y. How do we solve for x? Or how do we get y by itself? Well, we finally realize that, well, we need to make up a function because mathematically it's kind of complicated. Let's just say we invent this function. We're going to call it log 2. Log base 2 of x equals y. It's the same as saying x equals 2 to the y. These are exactly the equivalent equations. They call this function log. And what this means is, what x, when we take 2 to that power, will give us y? What x, when we take 2 to the power of x, will give us y? Let's look at an example. 2 log base 2 of 16. What is that? 2 to what number? Or sorry. Log base 2 of 2 to what power gives us 16? See, it's easy to mess up when you're lecturing. 2 to what power gives us 16? Can you figure out what that would be? 2 to what power gives us 16? Well, let's just go to our powers. We have 2 to the 0 equals 1. 2 to the 1 equals 2. Double that, 4. Double that, 8. Double that, 16. What number was that? 1, 2, 3, 4. Oops. This is 2 to the 1. This is 2 to the 2. 2 to the 3. 2 to the 4. 2 to the 4 gives us 16. 2 to the 4 equals 16. Therefore, log base 2 of 16 equals 4. I had it right the first time. Let's take a look at this. There you go, I messed up. Log base 2 of x means 2 to what power gives us x. Think of that spiral. 2 to what power gives us x. So the question is, 2 to what power question mark equals 16. 2 to the 4th equals 16. Log base 2 of 16 then equals 4. So, basically, you can watch the video about Introduction to Logarithms, but we'll find out what we can do with logarithms is allow us to do really big numbers and really tiny numbers. They turn into addition problems. Just like the numbers of stars in the universe, we can figure out the number of atoms in the universe just by multiplying two really big numbers, and we simply are adding the exponents together. 10 to the 10th times 10 to the 11th equals 10 to the 21st. Oh, there's an error in the textbook. 10 to the 10th times 10 to the 11th is 10 to the 10 plus 11 equals 21. By adding 10 and 11, we solve the multiplication of huge numbers. Well, here's a multiplication of two numbers. If I recognize 9 times 27, I could go multiply that out, or I could recognize that that's 3 squared times 3 cubed. And I know from the rules of multiplying in exponents that that becomes 3 to the 5th. Now, of course, most textbooks aren't going to be satisfied with that. You have to feed that to your calculator or multiply it out. And you might find out that finding the actual final answer might be easy to multiply 9 times 27. I get 63 times 9 is 18 plus 6, 43. That might have been easy to multiply out by hand, but I can just feed this into my calculator. And let's just take a look at my favorite calculator out there at GeoGebra. And I can just put in my exponents 3, type in 3 first, 3 to the 5th power equals 243. My calculator can do that for me as well. And I think they actually do show you the calculation. Now we want to do this with any numbers. But we realize that exponent is related to logarithms in an inverse way, right? We actually found the inverse of x equals 2 to y equals 2 to the x, reversed x and y, and solve for y, and we call it log base of that number x equals y. It's going to be confusing until we do some practice numbers. So let's do some review of the rules, and then we'll do some practice numbers. Remember what we have here. Log a of x means a to what power will give us x. I just realized. Plug in. Goes down on me. Give me power these days. They give you a place to plug in to put the video in. And they give you a place for power. I did ask for a plug-in for your laptops too. I don't see this one here. There's one way over there where I could reach. This. Guess I'm going to have to bring an extension cord as well as. Let's see. If I unplug that, that's probably not PC. Well. Definitely going to need an extension cord for this course. I don't see any. You don't see any other powers on the back of this table? You plug that in. Down below there. On your right. Yeah, thanks. There you go. Sorry for that hassle. And you could still use power supplies for those, right? Save your batteries. I'll ask them again, see if they can give us power supplies. Alright. Saw the screen go dim. It may last, but I don't want to cut out in the middle. Okay, where were we? When you see that equation, remember that means a to what power? A to what power? The y power equals x. Sometimes we're given y. Sometimes we're given x. Sometimes you're given y and x and not a. But usually you're given a and you have to figure out the x or the y. Remember, this is the same as a to the y equals x. It's the same as saying log base a of x equals y. So think through that very carefully, because we'll be doing more problems with that. When you see log base a of x, a to what power gives us x? So let's do a few easy practice problems. Log base 10 of 100. What is log base 10 of 100? Did I hear 2? Yeah. It's 10 to the second power 2. If 10 to the second power equals 100, therefore log base 10 of 100 is 2. 10 to what power gives me 100? Log base 10 of the number of atoms in the universe. How many zeros were after that? About 82 zeros. So log base 10 of atoms in universe. Well, they tell us they think it's about 10 to the 80th. Well, then log base 10 of 10 to the 80th is 80. 10 to what power gives us that number? So you do log base 10s all the time. A very famous logarithm is the earthquake number. When you hear about an earthquake in Chile, I don't know where the latest earthquake has been, but Chile is very active. Around Alaska, it's been pretty active. You got the tsunamis that happen in some places. What scale is that called? California. Remember what they call that, the scale of the earthquake measurement? It's called the Richter Scale. What that means is every number on the Richter scale means that earthquake was 10 times more in vibration magnitude than the one number below. So Richter scale of 1, let's just say things vibrate half an inch. Richter scale of 2 means things are vibrating 5 inches. Richter scale of 3, things are vibrating 50 inches. Now I don't know if it's inches, how much of vibration is a Richter scale of 1. It's probably a really small number because Richter scale of 7 has hit, I think the worst earthquake in the world is like a Richter scale of 9. But that's 10 to the 9th larger than Richter scale of 1. So I'm pretty sure the Richter scale of 1 is just a tiny vibration, but it's not zero vibration. Maybe we're experiencing a Richter scale of 1 when a huge truck drives down University Avenue. I'm not sure how that compares to Richter scale of 1. But a Richter scale is a logarithmic scale. Each number is 10 times in vibration distance of the previous number on the Richter scale. So let's do a couple problems here and then see if we got it right. Rewrite log base 3. There's my thumbs. Log base 3 of x equals 4 in exponential form. Well, let's see. Remember this. A to the y equals x is what log base a of x means. So 3 to the 4th equals x. 3 to the 4th equals x. Now in this case, we just have to multiply out to figure out what x is. 3 times 3 is 9. That's 3 squared. So 3 squared times 3 squared is 9 times 9, which would be 81. But they don't ask to solve it. They just say rewrite that. Question? How about this one? Rewrite 5 squared equals 25 in log form. Well, see, now we're at this side of the equation. So we're at, remember this, log base a of x equals y means a to the y equals x. Well, 5 squared equals 25. So log base 5 of 25 equals 2. 5 to that power gets us that number. So think of that spiral. 5 to that power gives us that number. When I see this, that means a to the y gives me x. And then I can go back and forth between that. So remember, this is the most important general form. Log base a, that's the base of any number. Sometimes they'll put a b there because base of x equals y means a to the y power equals x. Either way, solve that problem. A to the y power gives us x is what this is asking. Sometimes they'll give you y, sometimes they'll give you x, and you have to solve for it. So 3 to the 4th equals x. Log base 5 of 25 equals 2. Got it right. Now, because we used base 10 all the time, log is usually means, even if you don't say base 10, usually when you say log, that means base 10. Natural log, it uses a different special number that mathematicians like even better. So on my GeoGebra calculator, I have the ln. I think they have it ln. Let's see what they have over on the GeoGebra calculator. They don't have it here, but if I go to the function part on my GeoGebra calculator, here I have a thing called log and a thing called ln. And they have another thing of log to any base that I want. So your calculator will have that as well. And they just show you in this example that we can calculate the log key. So they don't take long from using log base 10 to another number, a special number e. It's called natural log. And the mathematicians have a reason for this and makes their mathematics life better. But they, instead of using 10, they use a famous mathematical number called e. You don't have to worry about memorizing e. Us nerds will do that for competitions. All you need to know that the natural log x is basically log base e of any number x. And you can use our calculator to calculate natural log of 3. And I'll just do that. Natural log of 3 and log of 953. So to get natural log of 3, I just click the ln and put in my number 3. And I get 1.09. Let me zoom in on that a little bit for you. 1.09. That's telling me that e isn't a very big number. It's not far away from 3 because it's almost 1 when I take the natural log, meaning e to the almost, just a little bit more than 1 gives me 3. The other problem, the log of 953. Remember, log means without any number there, log is base 10. Before calculating it, can you guess what the log of 953 might be close to? It's just a little less than 1,000. And we know the log of 1,000 is 3 zeros after it. So that's a great way to check your answer or think about what log base 10 of 953 should be around. It's close to 3, but it's going to be less because 953 is only 47 away from 1,000. So let's guess that it's going to be like 2.9 something. Let's see what it actually is. Take log base 10, 953. In GeoGebra, as soon as I hit enter, it gives me the answer. 2.97, even closer to 3 than I expected. 2.98 rounded up. And so any number, you can just say, well, what's the closest power of 10? And this is what they're doing when they say the number of atoms in the universe. They say it's a really big number. Doesn't matter. It's between 80 zeros after the 10 or 81 zeros. It's just a huge number. We don't have to calculate the exact number because they don't know it either. They just know it within a few orders of magnitude. So just plugging in a few numbers into your calculator. Okay, time for a little break. Let's do a little brain break and let's do another practice problem. Pull out your little notes here. Just a little practice problem for a little bit of brain break from logarithms and we'll come back. Let's do something that is going to be on the quiz. Let's do something a little, let's do it. We'll do the similar thing to this and then we'll do one more. Since it's related to this, what would be f over g of x? Remember, I'll give you a little chance to think about that. What would that look like? We have f up here, x squared minus 36. G is x plus 6. What would be f over g of x? And there's a shortcut if you recognize something special about f of x. Give it a little start on your own. Pretend it's an exam and I'm not helping you. What would you start writing? You figure out what that would be. F over g of x. This is g. and this is f. What would you start with? Yeah, you put x squared minus 6 on the top, and you put x plus 6 on the bottom. Now, unless you recognize something special, you don't have to worry about simplifying this, doing any special division. But if you recognize with your little toolbox that I remember from my factoring that a square minus a square, 36 is 6 squared, I can recognize that that's x plus 6 times x minus 6. And then g of x is still on the bottom, x plus 6. I can simplify that to, well, x plus 6 divides out, and that simplifies to x minus 6. So if they said, calculate it, if you showed your work and they said, well, you must simplify it, but you only got this far, if you showed this in your work, you'd get partial credit. What's one note I need to make here to say f of x over g, f over g of x equals x minus 6? You recognize one thing I need to make a note of about certain values of x that are allowed. Even though this divides out, 0 divided by 0 is not allowed. So I would have to put in quotes or comments if they require me to. I'd say, for all x not equal to negative 6. When I get negative 6, it becomes 0 divided by 0, which is mathematically not allowed, does not exist. But I can get a number really, really close to negative 6 on either side, and I think I'm going to have a linear function. It's just going to be slope of 1, y-intercept of minus 6. So basically, the graph of that's going to be slope of 1, y-intercept of negative 6, but I'm going to have a little circle around where x is equal to negative 6. That would be the graph of that it follows a line, x minus 6, but it blows up at x equals to negative 6. You're not often given problems like that, but keep that in mind whenever you do happen to divide by a number that you have to make a note of. Yeah, I can't let that be 0. I need to make a note of that's not an allowed value for x. Everywhere else, x plus 6 divides out. Here's a quick way to erase. All right, that was related to the last one. Let's give you a little simpler review problem. An inverse practice problem. Here we go. We have an inverse practice problem. F of x. Turned off my pencil when I cleared it. Turn back my pencil. Give it a good thickness. There, so it remembers my thickness good. Okay, so practice problem. F of x equals, put this on your blank sheet of paper, 7x plus 13. A little practice, a previous, giving our minds a rest from algorithms. Find f negative 1 of x. Remember how you approach this problem? First, take f of x, turn it into, put a y there instead. So you get y equals 7x plus 13. Then, switch your x and y's. So you get x equals 7y plus 13. And now solve for y. Do minus 13 on both sides. And now divide both sides by 7. 7's cancel out there, and I have x minus 13 over 7 equals y equals f negative 1 of x. Any questions about that? Want to make sure you can work that. Pretend it's an exam and you're working through this, you're nervous, but no, you've got it down. F of x, put a y there, swap x and y, solve for y. All right, before we get back to exponents, why do we have a violin here? Somebody left the violin here. I don't know why. How does this relate to exponents? Any idea? When I play a note, and I play the octave of that note, you are hearing twice the frequency, double the frequency of the first note. In our scale on the piano, it goes up by a half note. How many half notes there are in a scale? Well, the black keys, there's 5 black keys, and there's 7 white keys. Each note goes up 1/12 of the way, all the way up to the octave. Each note on a half note scale, 12 half notes, is 2 to the 1/12 higher than the next note in frequency. That's the frequency of the sound you're hearing. And so by 12 notes, by the time you've gone to 12 notes, you're 2, 1 more power of 2 higher than the first one. And if you actually measured the distance on the string, you would see the distance on the string is half the distance. Half the distance up gives me 1 octave. Another half of that gives me another octave. And because the string likes to vibrate at integer intervals of its original length, you can find that octave just by touching that part on the string. And it plays, how much higher was that? An octave was twice. The next octave is 4 times. And the next octave, sometimes you'll hear the good violinists play that somewhere up here, is another 2 times that. So you are hearing exponential things when you're hearing the scale, especially when you're hearing the half note all the way up. Any of you do any musical instruments? Play the half notes all the way up in your practice, all the way up and down 1,000 times to warm up. You are playing exponential increase in the sound frequency you're hearing, which can be measured. You can get a tuner. It's measuring that, listening to that sound. Exponents everywhere. Another example was, well, we mentioned finances. In growth of the famous snail. Have you ever seen the snail shell with the spirally growth? That's exponential growth of that snail. It's tiny. It grows 5%. Its shell grows 5% larger. Each year or each measurement all along the way, that snail is growing 5%, and that shape of that shell is an exponential function in growing. It's a It's a famous spiral in math. Because so many things are related to increasing growth by a certain percent, or the earthquake magnitude. So many things related to exponents. So that's why they want you to know about it in algebra. Okay, back to exponentials now. There's rules about logarithms. Pretty basic rules. And remember, it's all related to, when we see this, let's just look at what that means. B to what power, b to the 1, equals b. That's what that is saying. Log base b of any number b is 1. Because we know that b to 1 to the 1 power equals b. That's just like, well, that's obvious. Well, it's not so obvious when you list it this way. But we're just practicing the properties of the algorithm, of logarithms. Log base b of b is always going to be 1. Log base 5 of 5, because I know that any number to the first power is that same number. Log base b of 1 means 0 is equal to 0. That's a rule, because I know that b, no matter what it is, to the 0th power, b to the 0th power, I know that's always going to be 1. Right? B to the 0th power equals 1. That's always going to be true. That's just, everyone knows that in math, that any number to the 0th power equals 1. Therefore, we know log base b of 1 is 0. Now, this one gets a little more complicated. B, well, this is basically saying that b to what power is what? Yeah, duh. B to the p equals b to the p, right? Because the logarithm of base b of b to the p is b to what power gives me that. So that's like an obvious identity. Now this one, b to this power gives me p. Well, remember, when I see this, I know that log base b of p is b to what power gives me p. B to this power gives me p. So remember how we had a to the y equals x, or a to the y equals x? No, so no, we had a to the x equals y. That's right. A to the x equals y. That's the same as a log base a of y equals x. Or if I do switch my x and y's, a to the y equals x, a log base a to what power gives me x. A to the y equals x. Remember, when I see log, it's always that number to that power gives me what's inside the parentheses. So if I switch my a's and x and y's around, I'll get that. A to what power gives me what's inside the parentheses. And this one basically says, well, that's basically saying the same thing. B to the log base b of p is basically saying b to the p power gives me that. So I get the answer. So now, using those properties, I can solve some problems using my calculator. Log base 4 of 1. I don't even have to use my calculator for that one. 4 to what power gives me 1? Well, any number to 0 is going to give me 1. So I'm going to know right away based on rule number 2. So I look at here, I say rule number 2, log base b of 1, any number to the 0th power gives me 1. So I can use that rule to know log base 4 of 1 is 0. Any number of log of 1 gives me 0. This one, 5 to what power gives me 5? Well, we know that 5 to the 1 power gives me 5. That's rule number, gives me 1. That's rule number 1. And using rule number 4, 7 to the power of log 7 of 9 is equal to 9. I don't come across needing this rule very often, but they give that to us. So I'll say this is not often used. Not often. But they give that to us. Something we'll have to keep in mind. There's more important rules that we're going to come down to, properties of logarithms. These are the basic properties. They're pretty obvious. The ones that are more important are the less obvious ones that we're going to be using to multiply big numbers. This is a good one to know if you don't have it on your calculator, that if a and b and x are real numbers, and they're not 1 because the log would be 0 of those, log base a of x is the same as log base b of x divided by log base b of a. So if I don't have log a in my calculator, but I do have log b, or log 10, I can say, okay, log base a of x is log of x divided by log of a. Or if I have natural log base a of x is natural log of x divided by natural log of a. Don't want to worry about you having to memorize the proof of this. That's for your trigonometry, proving things. This is just something to, if you don't have log base a in your calculator, just calculate log of x divided by log of a, and you'll get log base a. So if we don't have log base 3 or log base x of some number, I can do either log of 45 divided by log of 3 or natural log of 45 divided by log of 3. Well, let's just do that in my GeoGebra calculator just to prove it. Log base 3 of 45, I'll do natural log of 45 divided by natural log of 3. So remember, log 45 divided by log of 3 or natural log of 45 divided by log of 3 if you're given any base that you're looking for. Now, this is all giving us practice with logarithms, but they're going to be coming to even more important things. That the reason they use logarithms, they love it, is because they make other things so much easier. Let's do a few problems before we get to those, the real reasons that we love logarithms. Remember, whenever you see this, you know what to do. I can always go back and write this in my notes. Log base a of x equals y means a to the y equals x. I keep writing my a's wrong. A to the y equals x. Well, doesn't matter what letters are there. Remember our little spirally drawing too. T to the c equals s. Doesn't matter what letters there are. I see this and I know that, well, that means I'm looking for t to the c power to equal the number s. And you may have given me 2 of these numbers, and I need 2 of the numbers if I want to find the other one. But that's all that means. 4 to the a equals p. Well, remember my equation, log base a of x equals y means a to the y equals x. Well, I have for a and p, well, there's my, I can fill it in, log base something of something equals this. Well, 4 to the a equals p. 4 to the a power equals p. If that helps you to remember that, log of any base of something equals something. What that means is that something to that power equals that something. Might be easier to have a, x, and y in there, but you see that? Okay, that's where the base is to that power, a, gives me what I'm looking for, the log base 4 of. Now this one, what's going on? Now what do I do? Well, remember, if you don't see a number there, you know that that's base 10. If you don't see a number, read a 10 there. So again, remember, 10 to that power gives me that. So I can write that as 10 to the r equals c. So without a number, log means log base 10. Is it making sense? I know it's going to be confusing if it's the first time, so by going through practice problems little by little, again, you can just write down what you remember. Log base a of x equals y means a to the y equals x. I've got e to the x equals 5. Well, that means that's my base. Log base e, a to the y equals x, log base e of gives me 5. A to the y equals x. X is what it's giving me. 5 goes in there. My base is e. And because it's log base e, you can also write it as ln, natural log of 5 equals x. Whenever you see this, don't worry about having to calculate yourself. I mean, that's your calculator's job. Kind of like the square root. Some numbers you recognize, like natural log of e squared, would be 2. But otherwise, let our calculator worry about calculating natural log of 5. Again, throwing in different letters shouldn't throw me off as long as I remember log base a of x means a to the y equals x. Well, that number v to the p equals that. That's the equivalent equation. And just practicing through that, doesn't matter what letters those are, that's what that means. Oh, they give us a few more practice. Hoping we'll get to the, they're starting with, they haven't got to the most important part. I guess that's in the next lesson of why algorithms are so handy. I guess they're just giving us practice at this, making sure we want to get this down really well. I guess we'll do that. I do have the next piece there, but I want to be sure you really have this down first. Log base 7 of 7 to the 10th. Remember what this means. Let's just put an x there for fun. What I'm looking for is 7 to the x power equals what's inside the parentheses. Now, it would have been, I guess you could do this if it helps. That 7 to the 10th is in parentheses. So 7 to the x equals that 7 to the 10th. Well, x must be 10, right? When I write it this way, it makes it a little more obvious. x is 10. Well, we're going to learn that log base a of something to a power, I can bring that out, and when I'm basically turning multiplication into addition, just like we did with number of atoms in the universe. Just add up the zeros. Log base 3 of 81. Well, if you recognize 81 is 9 times 9, which is log base 3 of 3 squared times 3 squared, well, that's log base 3 of 3 to the 4th. Well, log base 3 of 3 to the 4th, I know that's going to be 4. If you wanted to do it in a calculator, it didn't say you couldn't use a calculator. I'll just go to my calculator and do log base 3 of 81. Enter. Oh yeah, check my answer with the calculator. But this does require you recognizing that 81 is something a power of 3. Without knowing that's a power of 3, you have to use your calculator. So recognizing powers, that's something that as you work with numbers, you start recognizing patterns. Otherwise, you just crank it into your calculator. Don't worry that you have to memorize and recognize 81 is a power of 3. I did that just because I'm a nerd, recognizing powers of 9. Log of 440, using the calculator. Don't even worry about recognizing powers. If you wanted to, you could do the check your answer. Like for this one, I might just think to myself, before I do it, I know I'm going to get something less than 3, because log of 1,000 is 3. Log of 100 is 2. So I know I'm going to get something between 2 and 3. Otherwise, I can just let my calculator do the work. And if I get something outside of between 2 and 3, I know I've messed up on the calculator. So I just go to my calculator and do 440, enter 440, and log base 10. Oh, I guess I have to log base 10 and then type 440. Log base 10, 440. Some calculators have you do the number and then click log base 10. There it is, a number between 2 and 3, 2.64, and do they say round up? I would round, let's see, 3 decimal places, 2.643, just by using my calculator. Don't have to worry about doing anything else but plug it into the calculator, 2.643. Log base 8 of 50. Now, I do have a log base 8, or log base of any number. So I'm going to use that one, and then I'm going to go back and practice that. Suppose I didn't have this on my calculator, and I only have ln or log. So let's go ahead and do log base 8 of 50. So I type in log base 8, arrow, and enter the 50. And let's see, I know 8 squared gives me 64, so it's going to be a little less than 2. As a 50 is close, pretty close to 64. What do I get? 1.881. But suppose I don't have log base, I only have ln or log on my calculator. Remember the rule? Go back and check our rule. When I have logarithms, remember my little logarithm rule. Log base a of x is either log of x over log of a or natural log of x over log of a. So let's do it with that technique. It'd be log of 50 divided by log of 8. Let's just do that. Log 50 divided by log 8. And I better get the same number. And I could do natural log of 50 divided by natural log of 8, and I better get the same number. So that's a really handy rule for your calculator. Otherwise, most modern calculators, or a lot of them, let you do log of base anything. But back in the day, we didn't have that. You only had natural log or log. You have to remember that rule. The change of base formula. Now, I'll have to check in the exam. See if you have some of these in the exam. We'll do maybe some for practice. Let's just end today just doing a couple practice problems. Just building up your skills for next week. Let's do a problem to build your skills. I'll do Control A, delete. And do just a few practice problems that I know are in there. It looks harder, but it's not much harder. If you have f of x, turn on my pencil. If you have f of x equals 1 over x plus 3. Find f negative 1 of x. It's going to be, guaranteed there's going to be at least a couple like this on the next exam. Remember, I see a variation, and every time you visit it, if you do it online, you will see variation. And just a reminder, review exams 1 and 2, you go back and take them, they will bump up your scores on exam 1 and 2. I will use your score to bump up your exam 1 and 2 results. Because your exam grades, I think, are like a third, and the homework grades are a third, and then the finals a third. I don't have the exact numbers memorized. Okay, what do? First thing we do is put a y there. Y equals 1 over x plus 3. Exchange the x and the y. X equals 1 over y plus 3. Now we got to get y by itself. Well, whenever you're dividing by something, remember we want to get that on top and not have denominators, because we want to eventually get y by itself. So multiply both sides by y plus 3, or you could recognize the cross products are equal. But let's just go ahead and do it multiplying both sides by y plus 3. So multiply this side by y plus 3, and multiply this side by y plus 3. That gives me those canceling out, and I get y plus 3 times x equals 1. Well, I guess I could have done that, divide both sides by x as well. So let's do that now. Divide by x, and I get y plus 3 equals 1 over x. And now get the 3 over on this side, so subtract 3 from both sides, and I get y by itself. Y equals 1 over x minus 3. Remember, we're subtracting 3 from everything. It doesn't become a 1 over the quantity x minus 3. There I have my f inverse. The y where the f of x is, switch the x and the y's. Now, what conditions here? We got to be careful here. What conditions do we have to make a note of? What are the allowed values of x? Or what are the not allowed values of x? I got to pay attention here. When I divide by y plus 3, x cannot be equal to negative 3. But otherwise, this is my solution. And of course, x can't be equal to 0 in this part of it, right? So I trade x can't be equal to negative 3 in my original f of x, because it blows up. in the inverse, x can never be equal to 0 because this function will blow up. So there's always, whenever you have some denominator and x or y is in the denominator, there's going to be a place where you don't have an allowed value because you can't be divided by 0. I think enough practice for you. Make sure your name's on that little note paper. A couple practice problems. Any comments? Too fast, too slow? High or low? Love your feedback because I want to help you get through this. And remember, you can go back. I've opened review exam 1 and 2. Opened up for you online. Have a wonderful day. Hey, you set them on the end there on the way out. And this will be uploaded. I'll end the recording. I'll upload it in an hour.